Good morning, and I'd like to thank the organizers for giving me the chance to present this work. It's a joint work with DQ at MIT and the team that I will present later on. Before I say more about this project, I'd like to give you some background about this. Dick and I, we are latecomers to the Sensam effort. Essentially, we submitted a pilot proposal 2 years ago. And so back then, we had a vision, and really, it was just purely a vision. And I'd like to share with you briefly what was submitted. So our proposal was indeed, about monitoring the environment with large numbers of, dynamic sensors. And so we proposed to design and develop a system with, robust monitoring, for large extents of the marine environment, and the idea was essentially to have swarming, dynamic cooperative swarm of mobile sensors. We looked at a large number of them, like 100 or more, and we considered small buoys. And saying that because most of the buoys you have in the environment tend to be, that are deployed, are typically bulky, expensive. So we were considering inexpensive, or like rather inexpensive buoys, and many of them. And of course, we had to work on how to dynamically deploy them, because many of the features we have in the environment, as Eric Adams showed, are like thermal plumes. They evolve over time. They are under currents and changing environments. So we were like that was the vision. Then last year, essentially 1 year ago, we had the Sensam Scientific Advisory Board in Singapore, and we got a chance 1 year into the project to just present some of the ongoing results. So what we had at that time, 1 year ago, was a first prototype, which is shown on that slide that was presented to the SAB. And we had some field results in Boston and in Singapore as well. That was it. So since then, this is just, I want to acknowledge the work of the team. We had a joint team from MIT and SUTD working on this, and there are like other people, and most of them are in the room. But we have other people from my team that have been helping on that project. So essentially, over the past 2 years, this is what we have accomplished. So I will present in greater details the goals and objectives, just going to piggyback on the vision we had 2 years ago, but essentially the same goals and expand on it. I will then, look at the robot itself, the autonomous buoy design, and then talk about the system, the swarm of buoys. The core of it, we have swarming, so this is control strategies. So I would say a few words about distributed communication, but I'd like to spend more time on showing you some of the interesting results we have obtained in terms of validations and specifically in terms of field test. All right, so goals and objectives, they were very much, and they are still very much aligned with the mission of Sensam, so that is pervasive monitoring of coastal and inland water environments. This was explained yesterday by Professor Whittle. And in our case, we are interested both in nearshore environments, and we are also interested in the reservoirs. Singapore has many of these reservoirs, and they are like interesting processes. PUB has several issues to deal with, and we felt like this system could be interesting for both coastal environments and reservoirs. So if you look at the existing solutions and techniques, essentially you have single autonomous surface vehicles. They tend to be expensive, large, we say very expensive. And of course, because they are like just one of them, they are limited in terms of the surface they can monitor. Now, if you try to look at larger extents of water, well, you can deploy an array of sensors, but this tends to be fixed. And the challenge is, do you have the right resolution? Are you capturing the features? Do you have your sensors at the right location? And having a lot of sensors is going to be very expensive, and then most of the time, you will have many sensors that are going to be useless. So we felt, and we still feel, that there was a real pressing need for small, low-cost, and rapidly redeployable autonomous buoys. These two systems, the single ASV, it's not going to be a good job at going to the place of interest. And the fixed array of sensor, as we said, it's going to be very hard to scale it to a large environment to monitor. So that's why we were interested in tracking some dynamic features in the environment. What happens when you have something like a thermal plume, or if you have an oil spill, variations in pH and salinity, for instance, in some of the reservoirs in Singapore. That's like for Marina Bay Reservoir, it's a big challenge. Do you want to know if there is an influx of salt, where it's coming from, and other examples again that were presented yesterday by Professor Whittle. Problems of algae bloom. These are just motivations. I'm not saying that we have found a solution for that, but we have a system that is capable, with some extensions to look into tracking these dynamic features in the environment. All right, so let me first give you a snapshot of the overall system design before I delve into the details. So we use the multi-robot system approach. And our system is called Bob, right? That's his nickname. There are many reasons why it's called Bob, but band of buoys, bunch of buoys, and many others that I won't mention today. But essentially for Bob, what do we have? We have a bunch of mobile autonomous buoys. They are versatile in terms of sensing. I'll say a few more words about the sensors that we have been able to equip that buoy with. There is distributed communication. That's a technical aspect, but it's quite fundamental. And of course, at the core of it, what we have is these control strategies, cooperative control. And by that, I mean swarming. Okay, that's what it is in the biological world. So why swarming? Why is that so important to that problem? But number one is, as we said before, it's a problem of scalability. Okay, today I'm going to work on a marina reservoir, then I know how many buoys I need to have, but tomorrow I need to go into a larger lake. Will my system be able to scale to that environment? And if I want to go to the marine environment, then it's even larger. So this issue of scalability is very important, and many systems, they are like designed and limited to a given size of system. So for swarming systems, they are like theoretically scalable to any size. Robustness is very important as well. I think all of you agree with me that when you deploy something in the marine environment, well, it's very hard to get it back, to fix it. Agencies like NASA, for instance, when they send something into space and it breaks down, it's a disaster. So of course, the idea here is that if you have many of these units and one or two or more breaking down, well, at least your system continues to operate. So robustness is something that it's a feature that we really wish to have. And flexibility, all right, so I'm using the specific word by, swarm roboticists. So flexibility means that the system is capable of adapting to changes in the environment, all right? You have changing circumstances, and then your system will by itself be able to adapt to it. And if I go back to my slide on goals and objectives, since we want to track a dynamic feature in the environment, well, we want the system to be able to sense the environment and react upon it and then move in the right direction. So flexibility, or people call this swarm intelligence, but I think it's a bit of a buzzword. Flexibility is really something that is interesting to achieve this dynamic tracking that we're looking for. Right. So I'm going to delve into the details, and this is a very busy slide, but it's on purpose, right? It's a laundry list. So typically laundry lists tend to be busy, but this is just to show you all the things that we have taken into consideration. So at this point, I'd like to say that the original buoy is coming from Professor Yu's group at MIT. It was meant to do something else, and I'm not going to say what, but essentially it was evolved and redesigned to fit the purpose of that project. So what exactly do we have on our laundry list? Well, we wanted it to be compact, all right? Big, bulky buoys are already, in the ocean, and they are very hard to redeploy. There are like technical considerations for us. When we go to the field, if you have to carry 50 enormous buoys, well, it's good for your exercise, but it's also like a bit of a problem. Storage is another practical issue as well. So we wanted to have something compact, right? Less than a meter. Right now, we are in the 30 centimeter size. It has to be omnidirectional, right? It's an autonomous surface vehicle, but it has no head, no tail. It's capable of moving in any direction, and this is thanks to vectorized propulsion system. Self-righting, of course. Robust. Okay, this robust is different from the robustness in swarming. It's robust in the sense that we want to test this not in the comfort of the lab, but in a real environment, right? You go at sea. We had a chance to go to the fantastic facility at St. John's Island, and Cyril Natio will say a bit more about this later on. But when you go to sea, biofouling, all these problems come into play, so you really have to consider that. It has to be low cost, right? Especially in Singapore, where everything, cost is very important. So we're proud to say that we essentially managed to do 50 units for the price of one. I'm not going to tell you the price of one. But essentially, we're pretty proud to have achieved that. Also, keep in mind that when you make 50 units, you have all these problems of like, quality control, ensuring that there is no variability in all the prototypes because they're supposed to work together. But it was like, I think we have been doing our job in keeping the budget pretty low. The system is also expandable, right? For future developments, if you want to make a new prototype, if you want to add more sensors. So we really we made the right choices in the beginning such that we've been able later on to add more features to the system. It's also like computationally powerful. So you're probably wondering why I'm putting this. This sounds very much like a marketing, a brochure. But this is very important. We want to have a computer on board because there is a lot of computation to be performed, not just by the controller when you do swarming, but when you do the data processing and how you can use this data simulation to essentially compute a model and then get the system to move in the right direction. So we have a single board computer which is almost as powerful as this MacBook Air. It's also versatile in sensing. We've been able to do temperature, pH, salinity, dissolved oxygen, and the software part is not just hardware. We had an initial software pack that was different, but we moved to the open system, ROS, Robotic Operating System, that we expanded, and I think that was a wise choice, yeah. All right, these are just a couple of snapshots, right? My previous slide was very busy with the laundry list, but now you can see the CAD model. We did the entire PCB design of the electronics. As an engineer, I cannot help but show this, schematic diagram. If you want to have more information, we have this paper that is going to appear in Autonomous Robots, and there are like 11 pages dedicated to all of this. So we've been very thorough in the analysis of that and the design. Right, let me move on to swarming. What is swarming? If you turn to nature, what we know, we see that, amoeba are doing that, bacteria are doing that, birds are flocking, schools are, fish are schooling. Essentially, these behaviors, these collective behaviors are emergent. They are the outcome of repeated local interactions between the different units. And that's exactly what we want to mimic, in a sense, with our system. So the goal for us is, of course, we're not interested in just copying what the birds are doing, right? There is no point, having a school of buoys. There is no predator, right, for our buoys. So we need to design a collective action that is relevant to the problem we're trying to solve. And the challenge, of course, is how do you map a global level collective action with local rules? Because what we do, what we change is what we define are the local rule at the buoy level. And this, turns out, to become an emergent behavior. So that part is rather complicated. So I'm going to show 2 slides now with simulations, right? And later on, you will see the actual behavior in the field. But essentially, the way we have been doing that is by having building blocks behaviors at the local level. And by putting together these building blocks, you are able to get a collective behavior at the system level. So if you look at School of Fish, for instance, typically what you have 3 basic behaviors: avoidance, alignment, attraction, the AAA, as people say in the field, nothing to do with the Automobile Association of the US, but yeah. What is it? Well, when fish are schooling, what they want is they want to travel together. So they tend to look at one another and average the direction of travel. So that's alignment. And at the same time, they feel comfortable if they are close to one another, all right? That's the goal when you have a predator attacking. Essentially, by being very close to one another, you're confusing the predator. So there is attraction, and attraction is it's coming from vision. They see one another and they get very close. And then you have pressure sensing. Fish have lateral line pressure sensors. And this pressure sensing allows them to maintain a very short distance between one another. So they don't bump into one another. So these are the kind of things, these are some building blocks that you have for fish that we want to mimic with the system. So when we do these cooperative control, we can perform simulations. So that's exactly what we have on that graph. So in these simulations, we have 49 buoys, all right? And these are, I want to say these are simulations, all right? These are point particles. They have perfect mobility, but still, we want to see how they react. So we start with, we have one intruder here, and this one wants to essentially go through the pack of these buoys, and we want the others to essentially move in order to give way to these buoys. So as you can see here in light gray, you have the trace, if you want, of these buoys. Those that are quite far away, they are essentially not moving. So it doesn't seem like a big deal, but all of this is decided by the agents themselves, right? So we don't tell them where to go. They decide where to go based on how the others are doing. So you can also do bypassing. You can also try to sneak in when you keep the buoys fixed. So we use a lot of these simulations essentially to guide us in the design of the swarming strategy. All right, I'm going to show another simulation here, and this one is interesting because we have performed the actual experiment in the field. So what do we have? This is the classical area coverage problem, where essentially you're given a surface and you put some agents in it and you want them to maximize the coverage of the area. So what we have here, we look into scalability issue. You go from 10 to 20 to 50, and then you see how the buoys are properly packed into it. Because it's a simulation, they are very nicely packed. But what we have been doing is we have been challenging that. This is essentially what people have been doing all along, right? But instead, what we're doing is we are changing over time the surface, the environment, the surface area that you have to cover. So we go from a disk to this kind of peanut shape. We chose that surface area because it's really challenging the system. So the buoys have to decide among themselves how to redistribute into this new shape. And of course, we look at that when you increase and change the number of buoys. Okay, I'm going to skip, for the sake of time, I'm going to skip distributed communication, but this is a very technical term. Essentially what we have a mesh network that allows us to push the information in the system, so there is no central controller. If we want to have robustness, the system has to be completely distributed. So the communication we have is entirely managed by the buoys themselves. Right. Let me go to the validation results. First test we did, okay, this is in the field now, right? It's not a simulation. What you see here, these are the dot represents the GPS tracking of each and every buoy. They start, their initial position in blue. The red dot represents halfway through the process of aggregation, and the black dot is the final position. So this seems like, we pushed on the button and all of them went into that direction. What I want to say is what we did is we put them in the water and then we told them, now you decide, you aggregate. All of this is based on a consensus algorithm, right? So we don't know where they are going to decide to go, right? So the buoys themselves decide collectively on the locus of aggregation, and that's what was achieved on a fairly large area. This was performed at Bedok Reservoir, by the way. All right, another test, which is also interesting, is it's a collective behavior called leader-follower. What you have is you have one buoy that you control, or you can say it's a selfish buoy doing its own behavior, and all the others are doing a consensus behavior. And you take control. So what we did is we took control of the buoy that has the tracking, the blue line here. And as you can see, all the others followed, except for that one. Right? So we're showing this one. This one ran, had a battery problem. And we highlighted this because this is showing robustness, right? There is one that is lagging behind, misbehaving. Well, the system, as you can see, it's not bothered by one that is left behind, all right? So I can reassure you that we got it back. We went with the kayak, and the kayak is not shown here, and we got the buoy back, but the system continued to operate properly. All right, let's go to the actual problem of dynamic area coverage. So this was performed again in a reservoir. What you have here is the field view. I wish we could have a top view, but you're not allowed to fly drones, so we're in this area, so unfortunately. So we have a side view. It's exactly matched. So you're going to see here the GPS position real time with the video in the field. It was raining on that day. Before I turn on the video, what is going to happen? Well, you're going to see that the buoys here, I think we have 20 of them, they're supposed to, in the field, they're supposed to map or cover this area, and this surface is going to change over time, and you will see how the system is going to respond. Right, there you go. So they're moving. I'm sorry, the video is not very good, so there's something that we need to improve here. But you see that the domain is changing into this peanut shape, and the buoys by themselves, right? We're just watching and taking pictures. They are redistributing themselves, and the system goes back to the disk. And again, the buoys decide what to do real time. I think we lost one as well, but the system continued to operate. If you lose one or two, we did that test as well. Well, essentially, they will redistribute in the space. Okay, right, that's nice. Now, a couple of results, and I'll just finish there. These are the views in the field that we have just seen. So we performed a scalability study. What happens when you inject more buoys over time? So we started with one, and then the only thing they have is a goal. You have this surface that you need to cover, and then we added more and more and more, and here you can see that this is a metric that measures the effectiveness of the system, and you see that your effectiveness, essentially, the effectiveness is the inverse of that, so your effectiveness increases when this decreases. This is based on the tessellation of the space. All of these are based on field results, right? Showing very good scalability. This is now showing flexibility, right? This is something that very few people we're very proud of this because very few people have been able to test the ability of a swarm robotic system to dynamically redeploy real time. So you go from the disk to the peanut shape, and in blue, we have what essentially the simulation will give us, which means that you have a perfect buoy, and our buoys are far from being perfect. So you have a perfect buoy, and you will obtain essentially this kind of metric, and our system performed quite well. Now, let me just conclude now. Essentially, this system, we received, some compliments from the reviewers, which is so rare these days that, I feel I should mention it. Right, and I can feel that I'm not the only one, having these experiences. And so we were pleasantly surprised to read that people were acknowledging that this was really state of the art. However, they had a couple of comments, but that's a fair game. So people are realizing this is a state of the art system, and the main reason, like 2 reviewers said exactly the same thing. Very few of these tests are actually carried out in unstructured environments, in the absence of any supporting systems. As I said, people typically do that in labs, and you have overhead cameras and things that are helping. No, this for our system, it was in the heat of Singapore, in the humidity, us sweating, especially my researchers, and the results are speak for themselves. Now, moving forward, we are going to start working on heterogeneous swarming. We have many ideas, but Pablo Valdivia is going to give a talk later on, and we just almost get a grant, right, to start working on his soft robots swarming with our buoys. So we're pretty excited about this. There is another thing I mentioned earlier, and I didn't say a lot about it, but essentially we wanted to do data assimilation. The buoys have sense data. We want the sense data to be on-the-fly processed. That's already the case, but we want this to be fed into a computational fluid dynamics system that will be computed by essentially the cluster at sea, and use that as a way to guide the swarming. And lastly, as well, related to our work with Pablo, we want to go underwater because the surface is nice, but there is a lot of things going on underwater. Thank you very much.
Okay, let's have the next speaker set up. Professor Whittle.
Roland, this is a great talk. Can you just comment, though, on you talked about scalability in terms of numbers of the sensors, but for me, scalability on the marine phenomena is on the physical scale. It's a very large scale. So I can imagine while you're communicating over relatively short distances, you're running tests over relatively short time periods, power is not really a big issue for you, power and communications. But if you were to extrapolate this to, you showed us a picture of the Barents Sea with an algal bloom, hundreds of miles, hundreds of kilometers. What does scalability mean on physical length and time scales for some of these big problems where you want to track big features? What challenges remain in dealing with that?
Yeah, that's a very good point. I indeed show this algae bloom on like several hundred kilometers, and our system right now is not capable of doing that. Even if you add many buoys, that's just like impossible. The challenges are, indeed the communication, right? There is no system right now that will allow you to deploy a network over such distances, and communication is paramount for that. So without that critical element of distributed communications over long distances, the system will not be able to perform. So I think at this point it's fair to say that what we have shown is limited to, I would say, several kilometers square, but not beyond that. Now, the scalability I mentioned in terms of the control, this one should be applicable to other systems. But that is, assuming that we have the technology in terms of the communication. And on that side, I skipped that slide because we didn't do much. We essentially used an existing technology. We had nobody in the team that had any knowledge in communication, but communicating in the field over long distances, this is a big challenge. Underwater is the same problem.